Hello dear students, welcome back to physics online class. So in previous session we were discussing about a Gauss law here. So by considering that continuous charge distribution, so we got that a linear charge density, surface charge density and volume charge density. So from the concept of a continuous charge distribution, so we come to know that electric flux, so that the word electric flux means the total number of electric field lines are passes through the given surface. Normally we can call it as a electric flux here. So in case of that electric flux, we got that equation for the electric flux. What is the equation for electric flux? So phi is equal to what? So phi is equal to E into d of s cos theta, where E represents that electric field strength and d of s represents that surface area and cos theta represents, so remember here cos theta represents that angle between electric field line and normal line. For example, if this is one surface, means if that electric field lines are passing in this direction, so theta represents that angle between electric field line and normal line. For this surface, which will be the normal line? Perpendicular line. So angle between electric field line and normal line, so that is theta here. So by taking that electric flux concept, so Gauss, he is the name of the scientist, he given that equation or he given a statement related to electrostatics, that is Gauss law in electrostatics. What is that Gauss law in electrostatics? The total electric flux through any closed surface is equal to 1 by epsilon naught times of the total charge enclosed by it. So from that Gauss law, phi is equal to what? Phi is equal to Q by epsilon naught here. So phi is equal to Q by epsilon naught. So in last class I derived this equation. So now let me consider what's the physical meaning I need to understand from this Gauss law here. Phi is equal to Q by epsilon naught. It means that electric flux is independent on the shape and size of the body. Whatever may be the shape and size of the body, flux value will be remains same. So remember one point here. So from this Gauss law, it clears that flux is independent. Flux is independent on shape and size of the body. Shape and size of the body. So for example, let me consider one sphere here. So for example, this is one sphere. So for example, if I place one charge particle at this point, so what will be the equation for flux value for this object? Flux phi is equal to what? Q by epsilon naught from that Gauss law. Instead of this, I will take one cylinder here. If I place the charge particle at this point here, so let Q be the charge placed inside the cylinder here. So phi is equal to what? Q by epsilon naught here. So for example, if I take one cube here, so I will place one charge particle here. For example, if I place one charge particle at this point, what is that flux value here? So flux phi is equal to Q by epsilon naught. So from this we come to know that flux value is remains same for that cube and for the cylinder and for the sphere, for the cylinder and for the cube, flux value will be remains same. It means that flux value is independent on the shape and size of the body, and it is also independent on position of the charge, where you are going to be placed inside the cube or inside the sphere or inside the cylinder. Wherever you may place the charge inside the cylinder or inside the sphere or inside the cube, so that flux value will be remains same here. So depends on these Gauss law. So let me consider one hemisphere here. So in case of that hemisphere, so that hemisphere is placed in a uniform electric field region, then I will consider that what is the value of electric flux through a curved surface. So let me write it here. Consider a hemisphere consider a hemisphere. So hemisphere means half of the sphere. Consider a hemisphere placed in uniform electric field. So that hemisphere I will place it in a uniform electric field. Consider a hemisphere placed in uniform electric field. Placed in uniform electric field. So that hemisphere I will place it in a uniform electric field. Then let me find out flux through a curved surface. Then I will find flux through curved surface. Flux through curved surface. Flux through curved surface. So these are all CET points, or competitive examinations. They may ask the questions on the basis of Gauss law. They will give the shape, or they will give one hemisphere. So let me calculate what is the flux through a curved surface. So consider a hemisphere, place it in a uniform electric field. Then flux through a curved surface when electric field is I will consider different cases. When electric field is, first case, parallel to the base. So what is the direction of electric field here? Depends upon the direction of the electric field, flux value is depends. Why? Because basically I know the equation for that electric flux here. So phi, d of phi is equal to what? E into d of s cos theta. Or for closed surface, so for a closed surface, what's the value here? So for closed surface integration of E into d of s cos theta here. So it means that, so flux values depends upon the angle between electric field and normal line. So if that electric field is, first case, parallel to the base. So if that electric field lines are parallel to the base, what is the flux through a hemisphere I will calculate. So first I will draw that hemisphere here. So for example, this is hemisphere. So for example, this is hemisphere. For this hemisphere, this is circular part or plane portion, and this is curve path here. So look at here. So my intention is to calculate that electric flux through a curved surface here. So which is curved surface here? So this is curved surface here, and this is plane surface or circular I will consider. Then, so in the first case I said electric field lines are parallel to the base. So which is that base here? So this is base. So electric field lines are parallel to the base. So electric field lines are parallel to the base means, so this is the direction of the electric field lines. So look at here. So electric field lines are parallel to the base I said. So first consideration I took that electric field lines are parallel to the base. If electric field lines are parallel to the base, then what is the flux through a curved surface I need to find out here. So for example, for this hemisphere, shall I draw that normal line here? So what is the normal line here? So this will be a normal line. So this is the normal line. So this is base means for this base, so this is one perpendicular line. So this perpendicular line is nothing but a normal line. Then what is the angle between electric field line and normal line? Did you get my point here? So look at here, theta represents that angle between electric field line and normal line. So remember one thing. So electric field is parallel to the base. So electric field is parallel to the base means what is the angle between electric field line and normal line? So this is the direction of electric field line. So this is the direction of the normal. What's the angle here? So here angle is 90 degrees. So don't get confused here. Parallel means don't take it as a zero. Here electric field lines are parallel to the base I mentioned. So parallel to the base means what? Perpendicular to the, so parallel to the base. So electric field lines are parallel to the base means perpendicular to the what? Perpendicular to the normal line. So hope you understand now. So electric field lines are parallel to the base, or in other way I can say electric field lines are perpendicular to the normal line. So if theta is equal to 90 degree, then total flux. So total flux is equal to flux through the curved surface. So this is curved surface plus flux through the circular surface. So let me consider flux through the curved surface plus flux through the plane surface, or plane surface also I can consider as a circular surface. So what's the total flux value? So total flux value will be 0. Why? Because the number of electric field lines are entering is equal to number of electric field lines are leaving here. So total flux value will be 0 here. What is the total flux value here? Total flux value is 0. If I take the total flux value as a 0 means, shall I rearrange this equation? Electric flux in case of a curved surface. My intention is to determine that flux through the curved surface. So flux through the curved surface is equal to minus of flux through the circular surface here. So from that Gauss law equation, or from that electric flux, so phi is equal to, shall I write it as E into d of s cos theta here? So let me write that equation. Flux through the curved surface is equal to, so wherever phi is there, so I shall rearrange as a, so E into d of s cos theta here. What is the value of theta here? So theta, say I said that angle between electric field line and normal line. So what is the angle between electric field line and normal line? Theta is 90 degree. Cos 90 means what? Cos 90 is equal to 0. So flux through the curved surface when the electric field lines are parallel to the base is 0. What is the flux through the curved surface here? Flux through the curved surface is 0. So did you get my point it here? So look at here. So if the field lines are parallel to the base, then angle between electric field line and normal line, so this angle is 90 degree. So if this angle is 90 degree means cos 90 is 0. So total flux through the curved surface is 0. Now let me consider another example. If the field lines are perpendicular to the base, so let me write that if the field lines are perpendicular to the base here, then what is the equation for flux through the curved surface here? So look at here, field lines are, first one parallel, so now perpendicular. Field lines are perpendicular to the base. So again let me draw on one hemisphere here. So this is hemisphere. So this is curved surface. So what is the direction of electric field lines? I said electric field lines are perpendicular to the base. So this is base means, for this base perpendicular means this is the direction of electric field lines. Let me draw on. These are all the direction of electric field lines. So this is the direction of the electric field lines here. So electric field lines are perpendicular to the base. So for this base, so shall I take this is the normal line? So this will be a normal line here. Now if that electric field lines are perpendicular to the base means, what is the angle between electric field line and normal line? So electric field is upward direction, normal line is downward direction. What is the angle here? Angle theta is 180 degrees. So hope you get it here. Theta value is how much? So theta value represents that angle between electric field line and normal line. What is the angle between electric field and normal line here? Theta value is 180 degree here. So similarly, so electric flux through the curved surface, shall I take directly here? Minus of electric flux through the circular face here. So electric flux through the curve is equal to, electric flux through the curved surface is equal to minus of electric flux through the circular surface. For the circular, what is the formula here? E into d of s cos theta. E into d of s cos theta here. So theta value is how much? So theta value is 180 degree here. So flux through the curved surface minus of E into. So what is that surface area here? So here surface area, so circular means, so that is pi r square. Area of the circle is pi r square. So E into wherever d of s is there. So shall I take it as a pi r square here? Pi into r square. Cos of 180 degree. What's the value of cos of 180 degree? So that is minus 1 here. So here also minus and here also minus. So flux through the curved surface, so that is equal to, flux through the curved surface is equal to E into pi r square. So let me write it here. What is that flux through the curved surface here? Flux through the curved surface is equal to E into pi r square when that electric field lines are parallel to the base. So this is the base I said. So electric field lines are parallel to the base means what is the angle between electric field line and the normal line? So angle between electric field and a normal line. So that angle is 180 degree. If I substitute that value, I got that flux through the curved surface here. So flux through the curved surface is equal to E into pi r square here. Now let me consider that one more example in case of that Gauss law. So I will consider one symmetrical surface here. So in case of that symmetrical surface, if the charge particle is placed at the center of the symmetrical surface, then so what is the electric flux through each half of the symmetrical surface? Then what's the value of electric flux in case of half of the symmetrical surface? So let me consider one spherical surface or whatever here. I will consider that symmetrical surface. So I will consider one symmetrical surface here. Consider a symmetrical surface. Consider a symmetrical surface and charge is placed at the center of this surface I said, and charge is placed at the center, then so if charge is placed at the center means so flux half of the surface is, then flux at half of the symmetrical surface. So symmetrical surface. So half of the symmetrical surface means I divided into two equal parts here. So symmetrical surface is divided into two equal parts means 1/2 or half of the flux value. So what's the value of electric flux? Flux phi is equal to q by epsilon naught. So if I in the denominator 2 is there means 2 by epsilon naught here. So hope you understand here. I will consider one symmetrical surface. For example, you may consider one cube here. So for example, or you may consider one spherical body. So in case of that spherical body, let me place one charge at the center of this sphere. So now I will divide that sphere into two equal parts. So let me divide that sphere into two equal parts here. Then what's that flux through each half of the symmetrical surface here? So each half means 1/2 phi. So it is equal to q divided by 2 epsilon naught here. For example, if that symmetrical surface having the number of faces, so for example I will consider cube here. Cube consists of how many faces here? That cube consists of 6 faces. Then what is that flux through each faces I need to calculate? So let me begins with, so in case of that electric flux, so I will consider symmetrical surface here. So in case of that symmetrical surface, what is that flux through each faces I need to calculate? So flux through each faces is generalized formula I will provide here. Flux through each faces, if that symmetrical surface having that n number of faces. So for example, so if symmetrical surface having n number of faces, then what is that flux through each face here? So let me write 1/n here, 1/n into phi. So it is equal to what? Q divided by n into epsilon naught. So this equation is applicable for a symmetrical surface if that symmetrical surface having that n number of the faces. So for example, I will consider one cube here. So in case of that cube, so I will consider one charge particle here. So if the charge particle is placed at the center of the cube, what is the total flux? Total flux is equal to, so phi is equal to q by epsilon naught. Then flux through each faces I will consider. So flux through each faces means cube consists of how many faces? So cube consists of 6 faces. Then flux through each face will be what? So phi is equal to what? Q divided by, wherever n is there, n indicates that number of faces. I said number of faces for the cube is 6, so q divided by 6 epsilon naught. So let me begin that example. I will consider one cubical body here. So in case of that cubical body, I will place the charge particle at the center of the cube. So for example, let me draw one cube here. So this is cube here. So look at here. So for example, if charge q is placed at the center of the cube, then what is the total electric flux? So from the Gauss law, so from the Gauss law I will calculate that. So total flux value phi is equal to q by epsilon naught here. So this is equation for total flux here. So first one is total flux. So total flux value phi is equal to, phi total is equal to q by epsilon naught. Flux through each phase I will consider. So flux through each phase. Flux through each phase. So flux through each phase means, for example, here if this is the charge means, for example, if it is a positive charge means electric field lines are going out here. So this is the direction of electric field lines. So flux through each phase. So for example, if charge is placed at the center means that charge is emerging that electric field lines. These electric field lines are in all possible direction. So if these electric field lines are in all possible direction means these electric field lines are coming out of the cube in all 6 possible ways. So in that one, so flux through each phase. So from the one phase, how many number of electric flux is coming out? So phi is equal to 1 by 6 into q by epsilon naught. So look at here. So this is the situation when that charge particle is placed at the center of the cube. So let me consider. So now charge particle is placed at the one of the face here. For example, I will choose one face here. So in this face, I will place the charge particle at center of the face. If the charge particle is placed at the center of the face. So for example, so this is the first situation. So charge particle is placed at the center of the cube. In that second one, charge particle is placed at center of the face. So charge particle is placed at the center of face, here. So let me draw that cube here. So this is one cube. So here I will consider one charge particle. So that charge particle is placed at the center of the face. So let q be the charge. So this charge particle is placed at the center of the face here. So for example, in order to get that closed charge, so or enclosed charge, let me draw another one imaginary cube here. So look at here. In case of that Gaussian surface, so I need to consider that enclosed charge here. For making it as an enclosed charge, one more imaginary cube is required here. So parallel to this, one more cube is required. If one more cube is present means this charge is enclosed. So in case of that Gaussian surface, I need to consider that enclosed charge. For getting that enclosed charge, I will consider one more cube here. So one more cube I need to draw here. I will consider directly here. So if I take that one more cube here, so parallel to this cube, if I consider one more imaginary cube, now the charge is enclosed here. So did you get my point here? So in case of that Gauss law, so I will consider that enclosed charge here. So if the charge is present at this face, means I need to make that enclose here. For closing this charge, I will consider one more imaginary cube here. Then total flux value. So first I will consider that total flux value. So total flux value will be remain same. So phi total flux is equal to Q by epsilon naught here. What is the total flux here? So total flux phi total is equal to Q by epsilon naught here. Flux through the cube here, flux through the given cube. So from the given cube, flux through the given cube, flux through the given cube here. So how many cubes are present here? So in order to make it as a closed one, so here there are two possible, means two possible cube here. So two cubes are present. Then what is the equation for flux through the given cube here? So flux through the given cube is equal to what? So how many cubes are present here? So let me take that cube. So 1 by 2 Q by epsilon naught here. Why should I take that 1 by 2 here? Why? Because here two cubes are possible in order to make the charge as a closed one. So in order to make this charge as a enclosed, so there are two cubes are possible. So from that another one imaginary cube, so this charge will be getting closed here. So for that purpose, so flux through the cube is half of Q by epsilon naught. So next situation I will consider here. Suppose if the charge particle is placed at the corner here. So if suppose in the third case I will consider charge particle. So that charge particle is placed at the corner of the cube. If charge particle is placed, so look at here, if charge particle is placed, if charge particle is placed at the corner of a cube. So if charge particle is placed at the corner of the cube, then, so let me draw a cube here again. So I will consider one charge particle. So that charge particle is placed at corner of the cube I said. So here this is the position of the charge particle. So let me place the charge particle at the corner. In that first case I consider the charge particle at the center of the cube. So in this second case I consider the charge particle at the center of the face. So now here I consider the charge particle at the corner here. So what is the total flux? So total flux value is, so total flux value phi total, so that is Q by epsilon naught. So flux through the cube I will consider. So here also you consider for making it close. So how many cube requires here? One more imaginary cube is required here. So did you get my point? In order to make this as a enclosed, for that enclosed charge in this position one more imaginary cube required. So I consider totally, so 2 cube here. So if I place the charge particle at the center of the cube, means in order to make this charge particle as a closed one, then how many imaginary cubes will require here? So did you get my point here? So I will place the charge particle at corner side here. So in order to make this charge particle as a closed one, for example, treat me, this is one cube here. Here I place the charge particle here. I want to make this charge particle as a closed one. In order to make this charge particle as a closed one, so how many cubes are required here? Here 8 cubes are required. So how many cubes are required here? 8 cubes. Already one cube is there. How many cubes will require here? So remaining imaginary cubes will be 7 here. So did you get my point here? So look at here, at the corner of cube you will place one charge particle here in order to make it as a closed here. So how many imaginary cubes will require here? 7 more imaginary cubes will require. Then how many total cubes? 8. Already first cube is there. So in order to make it as a closed one, so remaining 7 cubes will require. Then what's the total cube here? So totally 8 cubes are present. So here 1 cube is there. If you place the charge particle at center of the face, 1 more imaginary cube required. So total cube will be 2 here. In the similar aspect, if the charge particle is placed at the corner of a cube, in order to make it closed 7 cube will require, then total cube will be 8 here. So in that diagram I will show that one. Here unable to draw that imaginary 7 cube. So let me directly show in the diagram. So in order to make this charge particle as a closed one, so totally how many imaginary cubes will require? 7 imaginary cube. Then what's the total cube here, including this one? 8 cube will require here. Then flux through the cube. So let me write flux through the cube here. So flux through the cube. How many imaginary cubes will require? 7 imaginary cubes. One is exact, means real cube. So total cube will be 8 here. So flux through the cube. So flux through the cube is equal to Q divided by 8 epsilon naught. What's the value here? Phi is equal to Q divided by 8 epsilon naught. Why I took that 8 here? So why? Because in order to make this charge as a closed one, so in the entire system totally 8 cubes are present. So that's what. So phi is equal to Q divided by 8 epsilon naught. Then what's that flux through the faces here? So I need to calculate flux through the face that is opposite to the charge. For example, this is one charge here. Opposite to the charges, I will consider that flux through the faces here. Flux through the face. Flux through the face here. Flux through the face opposite to charge Q. What kind of face I will choose here? That face must be opposite side of the charge. Wherever you will place the charge, I will take the face. That face is opposite to the charge here. Flux through the face opposite to charge Q here. Opposite to charge Q. So then what's the value of flux through the face? So which faces I will consider here? That faces must be opposite to the charge. So let me consider here. So in case of this corner, so here 7 imaginary cubes will present here. So out of 7 imaginary cube, I will consider that flux through each face here. So flux through each face here. So flux through each face means 1 cube consists of how many faces? So 1 cube consists of 6 faces. Out of 6 faces, only 3 faces are opposite to this charge. So look at here. In case of this charge, so I will consider that flux through each faces, that face is opposite to the charge I said. So these faces for this charge, so opposite faces means, so 1 cube means 6 faces I consider. Out of 6 faces, 3 faces are exposing. Remaining 3 faces are attached to the neighboring cubes here. So look at here. In case of that flux through this each cube, I will consider a charge particle Q at one corner here. So if the charge particle is placed at one of the corner means for example, so there are totally 8 cubes are present here. I will choose that faces. So in which manner I am choosing the faces here? That faces is opposite to the charge I said. So opposite to the charge means, so in that situation, so 1 cube consists of 6 faces. Out of 6 faces, 3 faces are exposing. Remaining 3 faces are attached to the neighboring faces. So that's what I will consider only 3 faces here. So look at here. In case of that flux through each face, so when the charge particle is placed at the corner, I will take only 3 faces here. Remaining 3 faces are attached with the neighboring cube. So that is what? So how many free faces here? Only 3 faces. So 3 free spaces. So 3 free faces means, so what's the cube value here? Q divided by 8 epsilon naught. So then flux through each phase will be what? Q divided by 8 into 3, 24 epsilon naught. So look at here, in case of that flux through that each phase, so phi is equal to Q divided by 24 epsilon naught. So remember here, if the charge particle is placed at the corner, total flux value will be Q by epsilon naught. Flux through the cube is, so Q divided by 8 epsilon naught. Why? Because 8 cubes will require for enclosing the charges. Then flux through the phases I will consider. Flux through the phases, which phase I am choosing here? Opposite to the charges. What type of phases I am choosing here? That phases must be opposite side of the charges here. The phases which is opposite to the charges means only 3 phases I will consider. Why? Because remaining phases are remaining phases are attached with the neighboring cube. So that is what, out of 6, just I will consider as a 3 phases here. So for 3 phases means f phi of phases, it is equal to Q by 8 epsilon naught whole by 3 here. So Q divided by 24 epsilon naught. So these are all the neat applications, just to remember the final formula, that's it. So no need to worry about that final, means no need to worry about why that 24 like that, just to remember that final formula. So phi in case of phases, Q divided by 24 epsilon naught.